Hi everyone, welcome back. Today we are going to talk about a new topic. Today we'll discuss oscillator theory. So I'll cover this over a series of videos. It's a very broad topic. I mean, I can literally make 50 videos probably if I start from the very basics, but I will try and cover it over a period of a few videos, just the theory part, and then we'll also go ahead and do some simulations on it later. But I'm kind of excited about this. It's a very interesting topic and sort of mathematically somewhat complicated. So it should be fun to discuss. Hopefully, you feel the same, at least after watching the first video. Okay, so it's a very broad topic. Many books have been written on oscillator theory, at least chapters for sure. And there are many papers on it. Historically, it's been developed a certain way, but in this video, I want to talk about it from a different perspective, sort of from a more mathematical perspective. Typically, it starts from a circuits perspectives in EE, but I think in my opinion, it is better to introduce the mathematical theory first that you need to understand it more deeply. So anyway, that's my personal opinion. So let's do it. Let's get into it. So in order to understand oscillators, the first or the biggest concept that I think one needs to cover is this idea of limit cycles. So today we'll discuss what is a limit cycle and qualitative behavior of limit cycles. Okay, so I'll assume that you have some background in calculus. So you've done maybe like introductory calculus, vector calculus. You don't really need vector calculus, but at least some level of differential equations is necessary. Okay, so what is an oscillator, right? So we'll discuss throughout the video, we'll see what is sort of a general definition or description of an oscillator. We'll differentiate the difference between oscillator and resonator, and we'll introduce this concept of limit cycles from a nonlinear dynamics point of view. Okay, so I'll leave a link in the description on a more traditional or a more rigorous introduction to limit cycles. You have to take a course on nonlinear dynamics, or you can read a book. There's an excellent book by Steven Strogatz, if you like. I'll leave a link in the description. There's also a really nice YouTube series from Professor Strogatz if you'd like to watch YouTube videos instead. Okay, so in this video, what we'll do is we will develop a qualitative description of limit cycles. And then in future videos, we'll make it more and more precise, more and more complicated, more and more quantitative rather. But just as a warm-up, this is a good place to start. Okay, so let's start with maybe the 1D case. Okay, so if I have a one-dimensional, let's say I have a variable, some variable x of t, I can write a 1D differential equation as x dot of t, which is dx of t dt, is equal to some function of x, right? So if this function is, it can be anything. Let's say it's like ax plus b, right? So dx of t over dt is ax plus b. So that's 1D differential equations, very familiar with that. One way to sort of deal with these equations is to deal with them qualitatively, especially if it's nonlinear. So for example, I mean, this is in fact a nonlinear, although it looks linear, this is in fact a nonlinear differential equation. So how do we show that? So what's the definition of linearity, right? We have to go back to that. So if I have f of x, then f of ax plus by should be equal to af of x plus b f of y, right? So this implies it's linear. Again, you can actually show that this equation doesn't satisfy that because of this constant term. Okay, so that's the 1D case. It's pretty straightforward. We can quickly move into the 2D case. So what is a 2D differential equation? Right, so I can write let's say given two variables, x and y, that are functions of time, right? You can say that, okay, they occupy some sort of space, right? So let's say, x belongs to real numbers and y also belongs to real numbers. So over time, x takes values in the real line and y also takes values in the real line. So then I can define the state of these variables in the xy plane, right? So this is sometimes called the phase plane or phase space, depending on, your background, I guess, or state space, right? So at any given point of time, the state of this system, which means the variables x and y, lie at some point of the space, right? And the dynamics, so how this point moves with time, let's say it moves along some trajectory, that is described by a set of equations, couple differential equations. We can write it as, x of t or x dot of t, which is the same thing as dx over dt, is equal to some ax plus by. And I can write dy over dt as y dot of t, which is some cx plus dy. So if you're familiar with this, you can also write this as vector in vector notation, right? So I can write x vector dot is equal to some matrix times the x vector, right? So this is the same thing as writing, for example, x of t, y of t is equal to a, b, c, d, and there should be dots here, x of t, y of t. Right, so this matrix A, essentially, once you solve it, you'll find how this vector A, vector x, evolves with time in this phase space, right? So this is kind of, at least in this case, it's linear differential equations, right? So these equations are linear. And you can show that they're linear using the definition above, okay? But it doesn't have to be linear. This A can be nonlinear as well. So let's take some examples, just to sort of make this a little bit more concrete. One example, let's do. So let's say, since we're doing in terms of electrical oscillators, let's take a simple LC resonator, C and L. And let's say this voltage across both of them is given by V, and then the current leaving the capacitor is given by I. Right? So then we know that, the equations for the capacitor are I equal to minus C dV by dt, because the current is going the other way. And the other equation is V equal to, sorry, L di over dt. Right? So here x and y are the same. So you can write this basically as Vi, and there's a dot on both of them, is equal to, let's see. So there's 0, 0 here, and V dot is minus 1 over C times I, and this should be 1 over L. And this is your V and I. Right, so since this is a linear differential equation, we know how to solve it, and you get the cosine and sine solutions or the complex exponential solutions. And that's fairly straightforward. But what I want to show is sort of more qualitative. So let's look at it more qualitatively. So let's see, just from the equations without actually solving it, is it possible to actually kind of map out qualitatively what the behavior would be in phase space, right? Because for nonlinear differential equations, this qualitative approach is in fact very powerful, because in many cases you can't solve the differential equation. So okay, I can say V is on the x-axis, and I can write either I here, or I can even write this as V dot, right? Because they're sort of just related by a scaling term. Okay, so let's say, my initial condition, or I'm looking at the time where I'm on the x-axis, on the v-axis. Then I know that v is positive, I is 0. And if v is positive, then these two equations should have a dot on them. If I know that if v is positive, then I dot is negative, right? And I dot being negative means that, oh no, sorry, these should not have dots on top of them. That's right. So if you look at this equation, if v is positive, then I dot is positive, right? Which means that if I dot is positive, we are moving in the positive I direction. Okay, so then let's take another point here where v is 0 and I is positive. Then we have to look at this equation because v is 0 and we have only positive I. Then v dot is negative, right? Or dv over dt is negative. So which means that point wants to move in this direction, in the negative v direction. If you pick this point, then of course it has to go down. And if you pick this point, same way you can show it has to go this way. And you can do the same thing sort of even for points like this. And you can show that these points would move like this. And if you plot it sort of for many points, you'll see that this trajectory is that of a circle. And for those of you who have studied circuit theory, this is fairly obvious that we know that in an LC resonator, when the capacitor is fully charged, there is no current through the inductor, which means when the voltage is maximum, the current is 0. And then when the current is flowing, the maximum current is flowing through the inductor, the capacitor is completely discharged, which is in this case. And if you plot, of course, the voltage of the current, which is a projection of looking at how this projection of the circle onto the x-axis or y-axis, then we see an I-sinusoid, right? And that's the same thing as, a circle going around this space forms a sinusoid by definition on either the x-axis or the y-axis. Right, so here we haven't solved any equation, but we found out what the qualitative behavior is in phase space, right? So, okay, that's good. So of course, the trajectory in phase space cannot be arbitrary, and you can actually show mathematically that from the theorem of existence and uniqueness that there are some weird cases that cannot exist, right? So if the function describing the differential equation is continuous, there are some more technical terms, but you can ignore them. For most cases, it is sort of continuously differentiable, and that's probably good enough. If it is continuously differentiable, then you can actually show that trajectories in phase space cannot intersect, for example. And an intuitive way to think about why they cannot intersect is that you can show that every solution in phase space needs to be unique for all t. So it needs to be unique for all time. So which means at a specific time, if you're here, now it has two solutions. It can go this way and this way, and that breaks uniqueness, right? So that's why, in phase trajectories or in phase space, you have some nice looking curves that cannot intersect each other. Okay. All right. So if you go back to this example, what we'll see here is that, so the value of this voltage and current at these points is kind of defined by how much charge or how much energy exists in the system, right? So if I put more charge on this capacitor, then we know Q equal to CV for a cap. So the voltage would be higher, and then it would take this trajectory, right? Or if the voltage is lower, then it would take this trajectory, right? So it's clear kind of here that, any solution, at least for this LC oscillator, any solution is valid, right? So for different values of the charge you put on the capacitor or different current through the inductor or different amount of energies in the system, you would have many solutions, right? And that should also be true, sort of more intuitive or mathematically. You can think of it in this way. So if I have some solution to this differential equation, V and I, right? Since it's linear, an alternative solution is some constant times VNI, right? So if I add some additional constant from linearity, this should also be a valid solution. And that's why from linearity, you can show that if you have this kind of circle, that's a solution, then a circle of any diameter should also be a solution. Okay, so that's about this LC oscillator case, or LC resonator, I should say, to be precise. It's not exactly an LC oscillator, as we'll see shortly. So let's look at what other dynamic behavior you can have on this phase space. Okay, so there are obviously some trivial ones. So for example, if I have, let's say this vector x dot is equal to 0 for all t, which means that, every point, no matter where it starts, it just remains there. Starts here, remains here, starts here, remains here, and it's completely static. So it's completely trivial, right? So you can think of this phase space as a plane, a complete flat plane, and there's a ball sitting on that plane. If it's a complete flat plane, then that ball doesn't move, right? So you can think of the potential over this entire phase space as constant, right? So the potential function of this phase space, which is this given by this equation, is constant, right? So that's a trivial example. And then we can take somewhat more interesting examples, I guess. So you can have, for example, an LC oscillator with some loss in it. So if I have an LC resonator with some resistor along it, you don't really need to solve anything. We know intuitively that this would spiral, right? This would be a spiral phase space. So you start anywhere, slowly starts losing energy and falls into the center, right? And you can take the opposite case. So if I have a negative R here, and it's the opposite, it essentially starts from here and then maybe draw it on the side. So it starts, let's say, from somewhere here and starts building up. So it's pumping energy into the system and it goes off to infinity, right? So it's obviously not very physical. And that's why having a negative resistance that's sort of absolute and independent of everything else is not realistic, because it would lead to infinite energy systems, right? So eventually, when this starts to grow beyond a certain point, other processes kick in, and then this is no longer a negative resistance. So I can have, for example, another phase space where the trajectories look something like this, right? I have some point at 0, and then sort of everything collapses onto this point, straight down, like this, right? So this point at the center is called a fixed point or stationary point. Or fixed point. So what does that mean? That means that this vector at 0 is equal to 0. That means anything that's over there doesn't move. And in fact, this is a stable fixed point because everything is moving into it, right? So you can have the opposite case where everything diverges from the center in all directions. So this is also a fixed point because if you're at the center, you don't go anywhere. But if you deviate even a little bit, then you start rolling away to infinity, right? So the potential function of the stable fixed point looks like a bowl maybe, or a valley. This is the 2D cut. So it would be like, in 3D, it would be like a bowl. So you put a ball anywhere and it rolls down to the center, right? Same way, rolls down. And for the unstable fixed point, the potential function would look like a mountain, right? So you put a ball here, it's stable, but if you roll it a little bit, it starts rolling downhill in all directions, right? So that's another case of a fixed point. You can have a fixed point along a line. So you can have a line of fixed points, for example. So you can have, let's say, dynamics that all flow to the y-axis this way. right? So this entire line is essentially a fixed point or set of fixed points, right? And if you think about it, I mean, the potential function of this would be like a valley, right? So you have a, let's say either a valley like this, maybe not like that, valley like this, and it has a gorge in the center, right? So it's like essentially just valleys coming down. So you roll a ball anywhere, it comes down and lands in the center. You roll over there, it comes down and lands in the center, and so on. Right? So that's also like qualitatively what you can have here. Maybe a more interesting example is that of a saddle point. So a saddle is where, let's say all of these lines are flowing this way. Right? So even on the x-axis, they flow out, but on the y-axis, they flow in. So this is called a saddle point. This is somewhat more interesting, less trivial, right? So if you're on the x-axis, you move along the x-axis away from the center. If you're on the y-axis, you converge into the center. Right? So for most points, actually, I mean, for most deviations, this kind of diverges to infinity. But if you deviate along the y-axis, it converges back. So that's interesting. And the potential function of this would look exactly like a saddle, right? So you have a valley in one cut and then a mountain in the other cut. So saddle is what, you know, they sit on, right, on a horse. So it looks like that. So that's a saddle point. And this is called the saddle point at the center. Okay, so we've seen that, okay, you know, we have all these dynamics and these are all for linear systems, right? So what about if I have a nonlinear system? Okay, so if I have a nonlinear system, there are some interesting kind of dynamics that you can see, right? So one obvious example is that, okay, you know, if I have a nonlinear system, it's most likely the case that if I have one solution that's a circle, you need not have any other solutions that are circles, right? And that's exactly what a limit cycle is really. And we'll see what that is. Okay, so let's say you know you have a nonlinear system. Or forget it for now, just forget about the fact that it's nonlinear. Let's say I give you some um, some state space like this or phase space, and I tell you that, okay, you know, there's a region. Let's say it's this kind of a region. Okay, it's like a donut region. So I'm talking about the region inside these two uh, shaded circles. If you tell you that everything outside this region, all the trajectories are flowing in to this region, sort of like this maybe. And even on the inside, everything is flowing into that region, right? So it's not possible, for example, for a line to go in there and get and cannot cross itself. We know that. So it has to like come in here and cannot escape. So every trajectory that enters this kind of donut uh, or annulus region cannot escape, right? So it's, and I also tell you, let's say, for example, that there are no fixed points in this region. So if this region has no fixed points as well of any kind. Right. So if I told you, okay, there's a fixed point here, then you could assume, okay, you know, all these lines are coming in and they all converge into this point. But if I tell you that there are no such fixed points, then the only other solution, actually, there's a theorem which says that the only other solution is that there has to be a stable trajectory inside, a stable closed trajectory. Right. So a stable closed trajectory is where everything that's coming in converges onto this trajectory. And once it gets onto that trajectory, it stays onto that trajectory. And that doesn't break uniqueness because at every point of this trajectory, of course, there's only one unique solution, right? So everything comes in there and converges onto this trajectory. And such closed trajectories or stable closed, it doesn't have to be stable, in fact. Such closed isolated trajectories, they're called. So an isolated closed trajectory is called a limit cycle. That's sort of the definition, right? And you can actually have unstable limit cycles too. So for example, I can have a system where, let's say I have a limit cycle, which means that if I'm on that cycle, it stays on that cycle. If I'm on the cycle, it stays on there. But if I deviate, it diverges to infinity or converges to the center. So these are not that interesting, honestly. What are more interesting are the stable ones. Okay, so I'll just erase that for now. So this is sort of a qualitative kind of introduction to limit cycles. It's actually very hard to show that given a nonlinear. Okay, let me first explain why it has to be nonlinear, right? So we know that if I have a closed trajectory or closed solution, it has to be in a nonlinear system, because if the system was linear, then any closed trajectory of, by scaling this down by a factor c, even this would have to be a solution, and even this would have to be a solution, and that's not possible, right? We saw that we started by saying that this is an isolated closed trajectory, and the fact that it's isolated comes from the fact that this has to be a nonlinear system. So I didn't prove that nonlinearity leads to limit cycles. I just showed that linearity cannot lead to limit cycles, which means that if there is an isolated closed trajectory or a limit cycle, it has to come from a nonlinear system. And that's actually one of the fundamental things that you need. Another thing that you can quickly or readily see is that you can't have such an isolated closed trajectory in 1D phase space, right? So if I just had a single line, of course, you cannot have an isolated closed trajectory, because then you have to come back, right? And that's not allowed. You can't self-intersect. So on actually a 1D phase space, you can only have trivial fixed points that are stable or unstable. You can't have these kind of closed trajectories. So the two necessary and not sufficient, the two necessary conditions for limit cycles are that it has to be nonlinear and it has to be at least two-dimensional, right? So these are the necessary conditions. They're not sufficient. So you can have nonlinear 2D or 3D or 10D differential equations that don't lead to limit cycle solutions. Okay, so coming back to LC oscillators, how do I make an oscillator out of an LC resonator? So that actually I want to specify the difference between the two. So if I just have this is actually not an oscillator. This is a resonator. Okay, you can still call it, I guess, an oscillator because it oscillates, but this is more like a pendulum, right? So it's not exactly self-sustaining, and it's not a self-sustaining oscillator. So that's like, some people call it an oscillator, some people call it a resonator. You can call it anything, but you need to understand conceptually what's the difference between this and a limit cycle. Right? So for a limit cycle, you actually need something like this. And then maybe you need like a negative resistance of some kind, which is a nonlinear resistance, right? So a nonlinear negative resistance. This is a very simplistic model. I mean, it's obviously more complicated than this, but the idea is like this, right? So you need some kind of nonlinearity, and typically that comes from a transistor, right? Yeah, and that's why, in fact, linear models of um, oscillators are not the best in studying them. So, okay. So an electrical oscillator is a stable limit cycle in phase space, right? Or has, I should say, maybe has a stable phase limit cycle, or you could also say is. Okay, and to really understand to understand the dynamics. What do I mean by dynamics? So things like phase noise, injection locking, or pulling, all these phenomena, etc. Maybe I'll say. We need to study the behavior of these limit cycles. All right, so we actually need to study the dynamics of limit cycles. So let me give you maybe a preview of what we're going to do. Okay, so let's say, I have some kind of oscillator, say VI again, and this is the stable limit cycle, right? It's a perfect circle. So then I know that if I look at the voltage, it would be perfectly sinusoidal, right? Which is just the projection of this limit cycle on the V-axis. Is that really true? That's only true if this trajectory around this circle has a constant angular velocity. And that's not necessarily true, right? So for example, if I'm stuck here, let's say I'm stuck here, and then I make a quick transition to here, and it's very slow in this region, and a quick transition, very slow here, quick transition, very slow here, and that would look something like a square wave. Right? At the same time, you could have a constant angular velocity and still have a square wave if the limit cycle looks like a square. Right? So it's not enough just to look at the shape of the limit cycle. You also need to look at the trajectory of phase along the limit cycle. Right? So the limit cycle obviously has like an amplitude factor, which is this, and it has a phase factor, right? So that's why studying these dynamics becomes very important. And we'll look at it more quantitatively as we go through. At the same time, you could also have some crazy looking limit cycle, right? Something like this maybe. In fact, the Van der Pol oscillator has a limit cycle that looks like that. So which means that from the shape, you can also tell that there's a lot of harmonic content, right? We know that this limit cycle is periodic, which means that it can be expanded in terms of a Fourier series, and which means that it has all these harmonics. So for example, if you want to make a oscillator that has higher harmonic content, let's say you want to extract the second harmonic or the third harmonic, then you need to be able to study the behavior of these limit cycles and the dynamics of these limit cycles, right? So that also becomes very important. Just to give you a preview of phase noise, which we'll be looking at next, that also can be easily understood in terms of limit cycles. So let's say I have, a limit cycle like this, right? And again, I have V, I have I. Oh, come on. I have V, I have I, right? So if I have some inductor, some capacitor, and something here, right? Some negative resistance of some kind. And you want to understand, okay, how sensitive is this to noise or phase fluctuations or some kind of injection of current. So if you model the noise as some kind of a nonlinear or some kind of a current source, right? My noise, let's say, then you can model this as some introducing some charge into the system, right? So you can show that you can actually intuitively see that, if the charge is sort of injected at this region, then the voltage jump happens when you're here, right? So you have, as this is going around, let's say it's coming back like this, and then at this point it jumps, and then it settles back into the limit cycle, right? So here you introduced a huge amount of amplitude shift. Right? And we know that a limit cycle can correct its amplitude variations, right? Because of course, all of these trajectories are converging back into this region, into the limit cycle itself. But if you introduce that charge when it's at this point, then you introduce mostly a phase shift, right? So maybe not at this point, let's say you're somewhere here. then you go this way because now the charge has moved the voltage back, or has changed the voltage in this direction, in the x direction. And now from this point to this point, if it has come from here to here, which means that mostly you have introduced a change in the phase. And hopefully from this, it should be clear, or from this understanding of limit cycles, it should be clear that any change, as long as it's along the trajectory or still on the trajectory, this phase change cannot be corrected for. Right? We've only seen that the amplitude change is corrected for, but phase changes are not corrected for, right? So that phase change persists. So depending on when you introduce this injection of charge during the limit cycle process, the response of the system is different, right? So in that sense, this function of the trajectory of the limit cycle as a function of the injection is time varying. So it depends on when you introduce uh, that charge. And from this, we'll derive what is known as the impulse sensitivity function, right? So essentially, we'll see, okay, how sensitive it is to impulses at different times during the limit cycle, right? So let me just mention that. So amplitude fluctuations are quickly corrected, so it's less sensitive. We'll make this more rigorous later, but phase fluctuations they persist. And that is actually why free running oscillators cannot provide a good timing reference, right? Because it's very sensitive to phase fluctuations. They're not corrected for, they persist, whereas it can maintain a constant amplitude. Okay, so there are obviously more technical questions with this. I said, okay, if there's an amplitude correction here, then it comes back. But of course, when you make an amplitude correction and it comes back, can we say that sort of a normal or orthogonal to this limit cycle, if I move, then there is no phase impact on the phase? And later on, actually, we'll see that that's not true. So if you do make an amplitude fluctuation, if you do make a perturbation to this limit cycle along the normal to the limit cycle, there is still indeed a phase error that persists, and we'll develop more complicated models beyond the impulse sensitivity function that deal with those with that issue. Another issue is that I said, okay, it's time varying, which is obvious, but is it linear? So for example, if I have, let's say I'm looking at a function that takes in some charge, Q, and gives me the phase error or phase change or amplitude and phase change, right? So if we're looking at this function, of course, we know that the oscillator itself is nonlinear, but if you look specifically at this function, is this linear? Which means that if I have, let's say, a small charge versus a large charge, is the change in amplitude and phase along the limit cycle, does it scale according to this, according to the size of charge that I introduce? And the ISF model actually assumes that this is true. So it assumes that this model, it's actually a linear time varying model, assumes that it is linear, and we'll actually show we'll discuss ISF in the later video. We'll discuss that is actually not exactly right. So this is also not a linear function, and we'll study how to analyze nonlinear nonlinearity in this function as well. So as we develop more complicated models. So that's sort of what you can look forward to, I guess, in this series of videos that I plan to make on oscillators. Um, it's quite a lot of math. I guess in the first introductory video, it's more qualitative, but in the next video, we'll probably talk a little bit about the impulse sensitivity function and how that gives us a decent model or a good model of phase noise. And probably also we'll look at another paper which gives us a model of injection locking and pulling. These two are kind of commonly occurring phenomena, I guess, in oscillators. And this is work that was done by Ali Hajimiri at Caltech. And when he was a grad student, and also one of his grad students, I guess, did some of the work on injection locking. Okay, and we look at this model. It's very useful, I guess, in getting some intuition, and it's also sort of elegant in terms of simplicity. So once we deal with ISF, maybe we'll also do a video, if I get the time, on how to simulate the ISF in Cadence. And then after that, we'll look at the PPV model. It's the projection, perturbative projection, uh, uh, something. Perturbative projection vector model, PPV model. So we'll also look at this model, and this is actually it's more mathematically difficult, I guess, more complicated, but probably more realistic. So it's closer to what you would see in a realistic oscillator. So we'll discuss both of these models, and we'll also look at other related works. I mean, there's a lot of literature in this area. So this was done mainly by Alper Demir, uh, also when he was a grad student, I think, or just after he finished grad school, something like that. So they're very interesting in mathematical, and for this work, we'll have to develop quite a bit of mathematical background because this uses stochastic differential equations as well. Differential equation, maybe some perturbation analysis, and also some nonlinear techniques, which is perturbation analysis, I suppose. Okay, so we'll build up that, and we'll show that, some of the assumptions that ISF model makes can be corrected for using the PPV model. Okay, so that's pretty much the relevant part, at least. One quick word I want to leave you with is that, this whole theory of nonlinear dynamics, this was just sort of a very brief introduction, I guess, of limit cycles. But what we discussed so far was, like, for example, fixed points and maybe even fixed lines and planes. We saw, like, okay, you can have a line of fixed points or a whole plane of fixed points, lines of planes and stuff. Planes. And we also saw that, okay, limit cycles. These are all called attractors, right? Which means that if you're there or if you're nearby, you can be attracted into these points, right? And fixed points can exist, yeah, or fixed lines can also exist in 1D case or 2D case. And we saw that limit cycles can only exist in the 2D case, right? And it has to be nonlinear. But you can show that actually you can't really have beyond this in the 2D case. You don't have anything beyond limit cycles or phase point or fixed points. Like, for example, you can't have a whole region which acts like a fixed point or a whole manifold. But if you're interested, you can show that when you go to 3D, you get another beast called a strange attractor. It's actually the technical term for it, right? So a strange attractor, I'm not going to go into it too much, but essentially it's a kind of fractal in phase space, right? So the trajectory is never closing in on itself. It sort of forms a space filling curve of some kind. And this is related to chaos. So you can show that when you have 3D nonlinear differential equations, you get chaos behavior. And chaos is it's a huge field right now in studying weather patterns, things like that. So it's very interesting. And I highly recommend people who are interested to read Strogatz's book or his YouTube videos, and gives you a very beautiful introduction to this entire area, which really inspired me as well. So I'd like to thank him for his video, and also those who are interested can read about it there in more detail. But this sort of preamble to limit cycles as a qualitative introduction to what a limit cycle is hopefully makes some sense. We'll sort of clean up these ideas more in future videos, and we'll develop more mathematical basis for all of these functions. So hopefully you're excited for this series. I don't want to just make it a theory-based series. I also want to do some cadence simulations, and we'll do that. So I've set up a cadence environment now that I can finally use to actually do some serious circuits or integrated circuits design. So that should be also kind of exciting. We'll see how to simulate and extract the impulse sensitivity function, the PPV function, and so on, using standard oscillators. And we'll also simulate different oscillator architectures and look at the results. So I hope you're excited about this. And if you have any questions or comments, please leave them in the comments below. Okay, thank you so much.